Dear student, today we shall discuss about the composition of functions. Look at the diagram. Let f is a function from the set A to the set B and g is a function from the set B to the set C. If x is an element in the set A, then it has an image in the set B under the mapping f. Let this image be f of x. Since G is a mapping from the set B to the set C, therefore f of x has an image in the set C under the mapping G, and this image is G of f of x. Thus, there exists a function from the set A to the set C. If x belongs to the set A, then its image under this new function is g of f of x, and this new function is called the composition of f and g, and we denote by this symbol GOF. Thus, if f is a function from the set A to the set B and g is a function from the set B to the set C, then a function g composition GOF, that is composition of f and g, is a function from the set A to the set C, and it is defined by GOF of x is equal to g of f of x for all x belongs to A. The domain of this new function is the set A, and range is the subset of the set C. Look here. Since f is a function from the set A to the set B, then the range set of the function f may be the set B or the subset of B. So you must remember G composition GOF exists if and only if the range of f is a subset of the domain of G. Similarly, FOG, that is composition of the functions G and f, exists if range of G is a subset of domain of f. You must keep it in mind. Now we study about the properties of composition of functions. First theorem is the composition of function is not commutative. That is, if f and g are two functions, then FOG may not be equal to GOF. Let us take an example. Let f is a function from R to R and g is another function from R to R, but defined by f of x is equal to x plus 1 and g of x is equal to x minus 1. We saw that FOG is equal to GOF. Here FOG of x is equal to f of g of x by definition. Now g of x is equal to x minus 1. So f of g of x is equal to f of x minus 1. Now f of x is equal to x minus 1. So f of x minus 1 is equal to x minus 1 plus 1, that is x. Again, GOF of x is equal to g of f of x by definition. So this is equal to g of f of x is x plus 1. So g of x plus 1. Again, g of x is equal to x minus 1. So this can be written as x plus 1 minus 1, that is x. So here we see that FOG of x is equal to GOF of x for all x belongs to R. That is, FOG is equal to GOF. That is, composition of the function g and f is equal to the composition of the function f and g. And here, since the image is x, so they are equal to identity function, that is IR. Now we take another example. Let f is a function from R to R and g is a function from R to R. be defined by f of x is equal to x square and g of x is equal to x plus 1. We show that f composition FOG is not equal to GOF. Clearly, FOG and GOF are both functions from R to R. Now, f of g of x is equal to, by definition, f of g of x. Now, g of x is equal to x plus 1. So, f of x plus 1. We can write f of g of x is equal to f of x plus 1. Again, f of x is equal to x square. So, f of x plus 1 is equal to x plus 1 x square, x plus 1 whole square. X plus 1 whole square, that is a square plus b square plus 2ab. By this formula we can write this as x square plus 1 square, that is 1, plus 2ab, that is 2 into x into 1, that is 2x, for all x belongs to R. Again, g of f of x is equal to g of f of x is equal to g of f of x, that is x square, so g of x square. Again, g of x is equal to x plus 1, so this can be written as g of x square is equal to x square plus 1 for all x belongs to R. Clearly, this and these are different, so we can write FOG is not equal to GOF for all x belongs to R. From these two examples, we can conclude that FOG and GOF are not equal in general. They may be equal, they may not be equal. Another theorem is the composition of function is associative. That is, if f, g and h are three functions such that FOG, OH and FOGOH exists, then FOG OH is equal to FOGOH. That is, composition of H with the function with the function FOG is equal to the composition of the functions GOH and F are equal. This property is called the associative property. Now we take an example. Consider the function f from n to n, that is set of natural number to set of natural number, and g is another mapping from the set n to the set n, and h is a function from n to the set R, defined as f of x is equal to 2x, g of y is equal to 3y plus 4, and h of z is equal to sin z for all x, y, z belongs to n. We have to show that HOGOF is equal to HOGOF. Clearly, these functions are functions from the set n to the set R. Now, GOF of x is equal to, by definition, g of f of x is equal to g of 2x, since f of x is equal to 2x. This is equal to 3 into 2x plus 4, since g of x is equal to 3x plus 4. So this is equal to 6x plus 4. Therefore, HOGOF of x is equal to h of this, that is h of 6x plus 4 is equal to, since h of x is equal to sin x, so this is equal to sin 6x plus 4. Again, HOG of x is equal to h of g of x. This is equal to h of, since g of x is equal to 3x plus 4, so this is equal to h of 3x plus 4. Again, h of x is equal to sin x, so this is equal to sin 3x plus 4. Therefore, HOG of 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 x is equal to HOG of f of x is equal to sin 3 f of x plus 4 is equal to sin f of x is equal to 2x, so this is equal to 3 into 2x plus 4, that is sin 6x plus 4. Therefore HOGOF is equal to HOGOF, that is composition of the two functions GOF and H is equal to composition of the two functions F and HOG. You must keep in mind the other statements of the theorem, like the composition of two bijections is a bijection. That is, if F and G are two bijective mappings or functions, then GOF is also a bijection or bijective functions. Again, if F is a function from the set A to the set B, then FOIA, that is identity functions or identity mapping on the set A, FOIA is equal to IBOF, IB that is identity functions or identity mapping on the set B is equal to F, that is the composition of any functions with the identity function is the function itself. If F is a function from A to the set B and G is a function from B to the set A with two functions such that GOF is equal to IA, that is identity function on the set A, then F is an injection and G is a surjection. The other statement of the theorem 6, let F is a function from the set A to the set B and G is a function from the set B to the set A with two functions such that FOG, that is composition of G and F, is equal to IB, that is identity function on the set B, then F is a surjection and G is an injection, that is F is a onto function and G is a injection, that is one-to-one function.